In this video, we'll continue discussing carboxylic acids and properties of carboxylic acids. And we'll first start with drawing the resonance structure, or a couple of resonance structures for carboxylic acid functional groups. Now we have a carbonyl, so we do have an electrophilic carbon because of that carbonyl. But the other oxygen that's part of the OH group is an electron donating group. And so we can show formally through resonance how this oxygen can donate electrons. It can create a double bond between the carbonyl carbon in itself and then break the double bond between the current carbonyl. And so if we draw the result of that resonance structure, we now have an additional pair of electrons on what was the carbonyl oxygen, so that now has a negative charge. Then we have a new double bond between carbon and the oxygen that's part of the OH group. And so this has a positive charge. This oxygen has a positive charge. In this structure, all atoms are still closed shell. So this is a significant resonance contributor compared to any open shell, any resonance structures that contain an atom with an open shell. So we have a oxygen, the OH group oxygen, that's electron donating, and we can see that through resonance. And then we could also draw another resonance structure where those electrons in that pi bond are owned by oxygen. We know that oxygen is more electronegative than carbon. And so if both oxygens own all electrons that could be in pi bonds, then we have our open shell carbon in that case. So here we have our carbocation, which is open shell. So here are three resonance structures that describe this electron delocalization in carboxylic acids. Electrons from both oxygens are delocalized. And so that means that for hybridization, this oxygen is sp2 hybridized, the carbon is sp2 hybridized, and this oxygen is kind of somewhere in between an sp3 and an sp2. We see it shown as sp3 in the first and third resonance structures, but those electrons, one pair of the electrons, can resonate into a pi bond. So an sp2 hybridization better describes the hybridization of that oxygen. So we've talked about resonance, we've talked about hybridization. One important feature of carboxylic acids is also that this carbonyl carbon is less electrophilic than the carbonyl carbon in aldehydes and ketones. And that is because of this oxygen, the OH group oxygen, that can donate electrons. So by definition, carboxylic acids have an OH group, and that oxygen in the OH group that's not double bonded to anything is electron donating. And so if we're comparing the carbonyl carbon in the carboxylic acid and the carbonyl carbon in an aldehyde or ketone, That electron donating R group makes that carbonyl carbon less electrophilic. Okay, so aldehydes and ketones have a more electrophilic carbonyl carbon in general. And now that doesn't mean we won't look into reactions of carboxylic acids at the carbonyl carbon. We will certainly do that. But overall, they're less reactive than the carbonyl carbons in aldehydes and ketones. Now, we've talked about polarities of carbonyls. So let's redraw a carboxylic acid, and I'm going to draw it kind of at an angle, and you'll see why in a moment. Okay, so we know there is a polar bond between this carbon and the carbonyl oxygen that puts a partial negative charge on that carbon. There's also a polar bond if we focus on the OH bond, where electron density is pulled away from hydrogen towards the oxygen, and that puts a partial positive charge on the hydrogen. Carbonyl compounds can also hydrogen bond. They can hydrogen bond with each other. The OH part of the molecule, that hydrogen is a hydrogen bonding donor. That hydrogen can participate in a hydrogen bond with other electronegative atoms. And then both oxygens are hydrogen bonding acceptors, so they can hydrogen bond with hydrogens from other molecules. And so carboxylic acids sometimes exist as what we call a dimer, where the carbonyl oxygen from one carboxylic acid molecule is hydrogen bonded, so a strong intermolecular force, to the hydrogen of another carboxylic acid molecule. And then the carbonyl oxygen of that same molecule is also hydrogen bonded to the hydrogen of that initial molecule. So these dotted lines represent a hydrogen bond, so a strong intermolecular force. And because of the shape and properties of carboxylic acids, they can sometimes exist as dimers, as hydrogen bonding dimers. The dimer indicates that there are two carboxylic acid molecules that are kind of linked together through this hydrogen bond. It's not a formal sharing of electrons, not a formal bond, but it is a strong intermolecular force between these molecules.